Hello, my name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we are hosting today's webinar on graphene dispersions. Before we get started, I just want to make you aware of the antitrust statement from the Graphene Council. We do represent the entire ecosystem and supply chain for graphene. That includes suppliers, producers, and end users. There are prohibited activities which are listed here in our antitrust statement, which apply to any meeting that takes place that's hosted or affiliated with the Graphene Council. So I thank you for being aware of that and respecting those regulations. The Graphene Council was founded in 2013 and today is the largest community for graphene producers, researchers, application developers, and end users. And we are pleased to host today's webinar and have you join us as part of our delivery of education. Here you have a partial list of our members, which includes research institutes and universities, as I mentioned, graphene producers and end users. We are the largest group for this sector in the world. Benefits of membership include being part of this global network. We also provide our organizational members with the Graphene Report, which is more than 600 pages covering every aspect of graphene production and commercial forms of material, including a profile of more than 200 companies that produce graphene materials. Now, today's session is going to be talking about how to actually use and apply graphene materials, in particular, how to disperse them into a host material. Graphene is extremely versatile and it's attracted a lot of interest because it has so many positive attributes. The problem that we've seen, and the reason why maybe some folks who have worked with graphene in the past have struggled, is that the dispersion process step of working with graphene is not extremely straightforward and is also a critical step. So for example, you could have extremely good graphene material, but if it's not dispersed properly into a host material for an end application, the end application will fail. And that would not be the fault of the material. That would be a deficiency in how to do the processing. And that's what we're going to talk about today. Just to have a primer for those of you who may not be that familiar with graphene materials, technically it's a one atom thick layer of carbon that's sp2 bonded in a lattice formation or in a crystal formation. The reason why it's attracted so much attention is it has exceptional properties, including electrical conductivity, transparency, thermal transfer, tensile strength, and flex. So it really has multifunctionality and is quite interesting from that perspective. This is an extremely high aspect ratio material. So graphene is about 1/3 of 1 nanometer in height at a single sheet, and can be in the horizontal plane dimensions, submicron to multiple micron lateral size. So it gives an extremely high aspect ratio, which in turn affects dispersibility and viscosity. In terms of commercial forms of graphene, because we always hear, okay, I have this graphene material, but it's not always a single layer material. It can be 1 to 3 layers of carbon, 2 to 5 layers of carbon, 2 to 10 layers of carbon. And graphene nanoplatelets might exceed 10 layers of carbon, but they still would be considered some form of commercial graphene material and certainly have commercial utility. And so each of these differences, not only in the layer size, but in the lateral size, have an impact on dispersibility. In addition to those forms that were described on this previous slide, you also have graphene oxides, which have approximately 35% by weight oxygen content, reduced graphene oxide, which is what it sounds like, a graphene oxide with the oxygen reduced or removed. That brings it down to about 5% oxygen by weight. Graphene can also be delivered in the form of a powder, a dry powder. It can be in a solvent or a solution, and it can be in the form of a paste. And so we have these different types of format to receive the material in. Graphene nanoplatelets, and then functionalized graphene, where we are adding or decorating the graphene either on the surface or on the edges with additional elements or compounds. And so that gives you a little bit of a background. Now, when it comes to dispersion, what we'd like to suggest as a way of thinking about this and organizing our thoughts, and the presentations you'll hear from our subject matter experts will follow this format, is to talk about a process approach. So what's the first thing you have to do is looking at the material characterization. And we want to be aware of the most common errors and issues in compounding or dispersing graphene materials. You have a range of dispersion methods that can be used. And then at the end, we have to verify, did we actually achieve a good dispersion? And so I'm not going to go into detail, but this is the framework that we will use. And on that material characterization, you have to understand what type of graphene you actually have. And of course, you need to understand the behavioral performance of the matrix you're putting it into, whether it be a liquid or a solid. Common issues include agglomeration, deformation, incorrect loading factors, using surfactants, or surfactants are left on the graphene material, and other impurities, viscosity and temperatures that are used, and also just nanomaterial handling, because I mentioned this is a material that's in the sub nanomaterial in one dimension or submicron. Dispersion methods include things like high shear mixing, melt mixing. You have sonication, twin screw extrusion, planetary mixers, ball milling, and other methods. And of course, these not only can be used on their own, but they can be used in combination and at different process stages. And then for dispersion verification, primarily we're looking at TEM and SEM visual verification, but you can always use, in addition to that, other rheological behavioral testing for the material to see if you've actually achieved a good dispersion before you go on to make your end product, which is actually the objective of doing all this, is to incorporate graphene into an application. So that gives you kind of the high level overview of how we're going to approach today's subject. And I'm very, very pleased to introduce our first panel or pair of subject matter experts, Dr. Adrian Potts, who's the CEO of Applied Graphene Materials, one of the leading companies in this area, and who have a great deal of knowledge and expertise in how to handle graphene material, including this dispersion method. And he's joined by Andy Gent from the UK. Adrian's in the United States, Andy's in the UK. And with that, I'm going to hand over Adrian. If you want to go ahead and unmute yourself and go ahead and share your screen, it's going to be all yours.
Welcome, everyone, and thanks for the opportunity to share with you a little bit about what we do at Applied Graphene Materials. So as Terence mentioned, we're a UK-based company. I'm the CEO with that company. Spend part of my time in the US and part in the UK. And then Andy, my co-presenter, is based in the UK. So we're a 10-year startup. It's our 10-year anniversary actually today. So some great achievements been made over the past years. We have offices in the USA, as I mentioned, and then distributors globally. And we're seeking to add to our distribution network in terms of creating the opportunity to make this materials technology more available. So Terence covered the background to a degree on this remarkable material called graphene. When you look at the single layer performance of that material, remarkable properties. The key thing in terms of practical application of this material is how you translate those properties into real applications. And one of the quotes from the Graphene Council in their commercialization report from this year is all of the tension that you have with this novel, remarkable technology, the right material, so picking the right type of graphene at the right price point, of course, and matching that with the specific application and the aspiration of performance that you're looking for. So in terms of range of materials, there's a whole raft of different materials in this space, as Terence was talking to earlier, just in terms of materials availability, from different degrees of functionalization right the way through to different formats, different morphologies. One of the key things, though, in our business model and the way that we've approached graphene manufacturing and then application of this technology is the dispersion technology is really the key means, the key method for realizing the remarkable performance that graphene has to offer. So we've seen this slide before. I won't dwell on this, but it's just covers some of the materials that we'll be talking to. As I said before, there are many different types of graphene in terms of your nano material additive that you're looking to add to your end-use material. We would say that equally important to that is understanding what you are trying to put the graphene into and what you're trying to achieve with that. So in other words, to make graphene work, if you can add graphene to the end-use application correctly, then you can make remarkable use of that material to great advantage in the end-use application. So the keys for us, and where we've done a huge amount of development work over the years, is about application technology and a clear understanding not just of the graphene material that you're trying to incorporate, but also the end use that the material is going into. What does that involve? It's not rocket science really, but a deep engagement with the end customer. The more information that we receive from our customers in terms of unpacking what they're trying to achieve, the better and the greater likelihood of success in terms of understanding objectives and needs. And whether that's the application of a standard dispersion that we have on offer off the shelf, or whether it's a customized solution that is end-use specific. That is typical of what we do and how we do it. Clearly, we need to back that engagement up with what we call how-to data. So how-to, it enables the easy use of this amazing material in the end user's application. So we have available on our website a whole load of technical application notes and data in terms of supporting what we're doing in our chosen field, supporting that how-to knowledge in terms of practical applications on how to assist you, the customer, in terms of incorporating this material in a meaningful and constructive way to achieve the great end result that you're looking for. We see ourselves also as part of the group that are very much involved in regulatory leadership on the use of nanomaterials and particularly graphene, particularly with regard to REACH regulations in Europe. Our particular chosen fields for us as a company are really looking at unlocking the use of graphene in 4 key areas, really. So coatings, technology, so paints and coatings, and utilizing the remarkable impermeability of graphene to work as a barrier material. Of composites, looking at the addition of graphene to things like carbon fiber composites to further enhance mechanical performance and other attributes, printable materials, and then thermal adhesives, so utilizing the thermal conductivity of this material in dispersed format to enhance end-use performance. And that's just a few out of the vast array of opportunities that graphene presents. So in terms of the particulars of what we manufacture, we're a manufacturer of graphene materials, 2 core types, and then we have a number of other products in the range as well. But just to touch on, in terms of the difference between just 2 different types of graphene. So on the left-hand side here, you see very platy material. We actually classify this as a reduced graphene oxide, composed of nanoplatelet plates, relatively thick, around 15 to 20 atomic layers. And, it's a kind of good general purpose material for use in a range of applications, whether that's composite materials or coatings technology. And typical loading levels that we would deploy this material in the end-use application would be at around 1/4 to around 1%. So we have to think through how we will deliver that type of doping into the end-use application. And that's what this presentation is all about. And on the right-hand side of this, a very different type of material named AGMP 35, low oxygen content, high carbon content, morphology-wise, very, very different. So thin, crumpled sheets, around 5 atomic layers thick, very, very low density, very high surface area. And in particular, we have used this material to great effect through our dispersion technology into the world of anti-corrosion coatings. Very low loadings that we use in those applications. So typically 0.025% up to about 0.1% in a paint formulation. Key attribute with this material is its impermeability and adding to the tortuosity through a coating compared to other materials that are typically used in a coating application. So it's a super efficient material, and at very low loading level we see a huge increase in the surface area compared to materials that are conventionally used. So just some of the flow really through this thought process for decision making on graphene. So first of all, why graphene? What could graphene do for me in terms of utilizing those performance attributes? Even in the graphene nanoplatelet form, the material still has remarkable performance. Huge surface area advantage, as we mentioned in the last slide, for example, over other fillers. The aspect ratio advantage, the conductivity, the mechanical performance, thermal conductivity, and so on. The right form of graphene, what am I hoping to achieve in the end application that I'm looking to add graphene to? The key characteristics that I'm looking to improve the performance with. So what are my target properties through the integration of graphene? And then we get onto the key question of how am I going to integrate this material into my end manufactured product? What's the format of what I'm trying to achieve, and how do I add performance to that? So what's the material that I'm looking to add to? Is it a thermoplastic or liquid resin system and thermoset, elastomers, oils, a foam structure, or composite material? And really the key question is, how could I best introduce graphene into this format? And conversely, what are the best things that I can do to avoid failure? Further things to do with graphene, am I okay using a nano powder at all? There are a number of production environments where nanomaterials are frowned on, and we'll talk to a little more about that in one of the later slides. If we're using a dispersion, what would be the best option to deliver the graphene into the target material? And is that media compatible with the host material that we are putting it into? So we go to great pains in what we do at AGM to join all these dots together and answer all of these questions to enhance the opportunity for success. So understanding where the material will be used and when it will be added. So compatibility, not just with materials from a chemistry process, but how the material will be added and whether that will upset the balance of the rest of the formulation. It's absolutely critical that the material is added both in the right way and at the right stage. So for example, in the world of coatings, we have some great recommendations about not just offering this as a dispersion, but when to add it to the coating. And just about balance in terms of adding these very high aspect ratio, high surface area materials. It's very easy to, for example, to upset the balance of the end use product that you're looking to add this material to. So coming back to our experience in coatings, for example, we look at things like pigment volume concentration and the balance between solids and liquid resin and the ability of that resin to wet out all of the material that is in there. You start introducing high surface area materials into that equation, and it's easy to push that coating formulation over the edge and actually introduce porosity into the system. So we have to be very careful about how we balance what we offer with the end use application. So thinking through objectives in terms of our dispersion, loading level, some of the variables that we have in place. So loading level is a key area to control. And when you think about some of the very low loadings that I talked about earlier in the end use application, we want to match that with the ability of the formulator to have maximum flexibility in what they're doing. So what we aspire to is balancing that between what we put into the dispersion versus what is going to end up in the end use application. We also have to think carefully in collaboration with the customer about what happens to the rest of the dispersion. So if we're supplying something with, say, 10% graphene and it's 90% solvent, or a high percentage of solvent or water, we have to think about what happens to the rest of that material, the water or the solvent in this case, in that formulation, and how in some cases that has to be evaporated off, and how that will work in the end use application. Things like reactives, can we actually use reactive components of the end use formulation to use as the dispersion media to enhance the performance of the end use product? And then, is graphene actually replacing something? So are we using the dispersion to create the opportunity to replace other things in the end customer's application? Typical things that we look at in our world will be things like iron oxides and pigments generally, micas, and then functional materials in coatings such as zinc phosphates and chromates and so on. So a little more about dispersions and what do we actually want out of that? Clearly we need stability. We want the dispersion to be the same as received by the end customer as it is 3, 6, maybe 12 months down the line. Scalability of dispersion. It's easy to achieve great results with materials technology in the lab. We want to know and be confident that we can actually scale that process into larger volume. Other variables clearly have a huge influence on the end use application: viscosity of that dispersion, particle size, settling and agglomeration, and can I actually recover that, and the whole question of how will the material be used. So what do we want in the end customer's formulation? What are we aiming for? Clearly the utilization of graphene in terms of great utility, great functionality, is to achieve a separated array of graphene nanoplatelets as individual platelets in the end-use formulation. And those graphene platelets can then do the job intended, whether that's mechanical performance, thermal, electrical, and so on. We want a great separation of those graphene platelets in the end formulation. And that is what we're all about in the dispersion technology that we offer. Conversely, what are the things that we're trying to avoid? Clearly agglomeration, where the platelets actually end up sticking together. We end up with, just in simple terms, a filler rather than a high utility product in the end formulation. Sedimentation, and whether that's recoverable, or even crash out due to incompatibility of the dispersion in the end application. Just to touch on a few of those points, so dispersion stability. Key questions: is the dispersion stable? And does it sediment out? And what's the quality of that sedimentation? Can be recovered, and how? And we have some excellent guidance in our application notes on how to do that. And what are the implications for the end customer in terms of how to practically use this material? So typical at the bottom of this slide is what we see for just grabbing some data for some of our products. In this case, a dispersion of AGMP10, this very platy material, in a liquid epoxy, 12-month shelf life. And you can see at the bottom right in this slide, very good stability from a particle size standpoint in terms of stability of the dispersion. And the left-hand side, the upper graphic just describes what we aspire to in terms of stability of products. So a uniform dispersion with life, whether this is tested at 3 months, 6 months, or 12 months, we want to see uniformity of that dispersion with life. And we do a huge amount of testing in this regard. A bad result would be at the bottom left of this slide, where we see clear initially pooling of, in this case, a solvent dispersion, and the graphene ending up at the bottom of the bottle. Clearly, we don't want that, and we do a lot of work in terms of achieving stable and uniform dispersions. Viscosity. So viscosity of the dispersion, clearly one of the key questions is whether that's fit for end use purpose. So considerations that come into play here: particle size of platelets, surface area of platelets, and if you recall back to the earlier slide, huge differences in terms of morphology of material, the way that wets out and the way that the surface area interacts in the dispersion. The chemistry on the platelets, Terence talked to that in terms of oxygen content, for example, and that has a unique effect on dispersibility, and that in turn an effect on viscosity as well. Loading levels clearly again have a critical effect on viscosity, and a knock-on effect on formulating flexibility. So again, just joining all those together, what's the end user's process? How do we engage with the end user's process to understand what are the constraints and what are the limitations on how to use this material effectively? We have guidelines. Typically in coatings, we recommend adding graphene dispersions at the letdown stage of the manufacture process after all of the grinding of the fillers, just as a practical example of how to use this material effectively. So how does particle size distribution, looking at particle size for a moment, impact the end-use applications? What are the clearly considerations in terms of aspect ratio and actual physical particle size, and how this fits with the end-use application? So to pick the example of composite materials, when we look at things like fiber diameter, for example, versus the size of graphene particles versus the volume fraction that we are going to be applying, both of the carbon fiber in the case of a carbon fiber composite and the volume fraction of graphene that we're going to be adding, and how all that interacts together in terms of what we are looking to achieve. The example in coatings, aspect ratio is a huge issue for barrier performance, but other aspects as well, such as conductivity and mechanical performance and the flexibility of paints. We can see a nice example in the middle left of this chart, just in terms of the ability to dial in particle size. And we can do that through the range of processing methods that we employ in manufacture of dispersions. So starting with the base material, which has a fairly broad, the blue line, a fairly broad spectrum in terms of particle size, from a little over a micron up to 100 microns, and then able to dial that in very effectively through process technology using a range of process methods. Where does this all end up? Clearly we have dispersion products that we offer to the market, and our principal product offering is in two forms really. Standard dispersion, so balancing the graphene type, the loading level, the particle size, the viscosity, the stability. We have a range of standard dispersions in a range of different epoxies, solvents, water, and so on. And then custom dispersions as well, and masterbatches to suit the end-use application. Terence talked about some of the common issues related to dispersion technology, and there are clear things to be at least cognizant of in terms of understanding how you're going to deploy these materials in practical applications. Agglomeration is a key one to be avoided, and that in and of itself is challenging to undo in the dispersion, let alone in the finished formulation, and we would have to do a lot of work with that dispersion to undo agglomeration. Deformation, so being aware of the grind of the material and particularly avoiding grinding the material too far. Particle size and aspect ratio are important features in the utilization of these nanoplatelets in the end-use application. Loading level clearly has a huge influence on cause and effect in the end application. Use of other materials, so surfactants and so on, clearly there's a great opportunity to do that, to produce a custom dispersion to suit, but we want to carefully select those and ensure compatibility with the end application. Color, graphene is a remarkable UV blocker, and a small addition of graphene can add to a strong color shift, both in the dispersion that we have to offer, but also in the end use application. Maybe not so important in some applications, but certainly in the world of coatings, where you're looking to manage color in a top coat application, for example, or in a direct to metal coating, coloration can be an important consideration. And, we have to admit that graphene isn't suitable for use in every application. Impurities from process clearly need to be avoided, viscosity issues, and then nanomaterial handling. We touched on this earlier. Safe use of nanomaterials is crucial. That's why we've approached the business the way that we have, in terms of putting graphene into dispersion to enhance its safe use and give confidence to the end user about use of this material. A lot's been done, particularly in our work in coatings technology, not just in safe use of dispersions, but also in practical applications for sprayable coatings, whether that's aerosol or whether it's larger volume spraying. And just to touch on nanomaterial handling, whether it's REACH or TSCA accreditation, or the whole deal related to high aspect ratio nanomaterials, there are clear questions to ask. So what's the nano form of graphene in question? So coming back to the particular material, is it actually graphene at all, or is it a nanographite or an exfoliated product? What exactly are we dealing with, and what is the particular nano form of graphene that we are looking at? Related to that is whether there's read across from the toxicology data that we have in available to us. What are the volume effects and the supporting data that are required with that, because there are clear thresholds in regulatory approval whereby larger volumes require more and more data to support the safe use of these materials. And then, at the other end of the spectrum, to satisfy the end user's concerns, we want to understand what happens to the graphene in the end product. And clearly, our focus with that is on safe use of graphene in the workplace. And we see that as a major milestone and being crucial to adoption of this technology. We've done a huge amount of work in this area, looking, as I mentioned before, sprayable coatings, and proving to ourselves and proving to the community that graphene stays put in sprayable coatings and doesn't become a free material in those types of applications. So just looking at methodology briefly, we can do, as Terence mentioned earlier, all manner of different methods and use of those in combination to manage the things that we've talked about: viscosity, particle size. Just as a brief example on linked effects from processing, just very briefly, just looking at viscosity effects. So this is with very high surface area material on the left-hand side. Viscosity needs to be managed, as we talked to before, in terms of loading level. And the bars on this chart are around sheet resistivity, surface resistivity, or conductivity. And with loading level, we can see a nice reduction in resistivity with loading level. Managing particle size in the middle of this chart. So for a given particle size, we can see the effect of loading level, in this case on conductivity or resistivity. And then for particle size impact, in terms of multiple milling, where we're looking at process technology and looking at the number of milling cycles that we would run with this material. Clearly, larger platelets have a good effect for conductivity and managing resistivity. Lastly, and just my bit before I hand over to Andy, just for a brief wrap-up of our section. So dispersion verification, and this is so important, not just looking at what we have in the dispersion, but for quality control, for volume manufacturing. Clearly, suffice it to say, we can manage this process well with a whole raft of different methodologies to understand the quality aspects of dispersion. We utilize TEM and SEM. Clearly, those are great tools to look at powders, viscometry, UV analysis, mechanicals, electrical testing, thermal analysis are key things that we do routinely on dispersions and end-use applications to prove out the quality and the consistency of these dispersed materials. With that, I'm briefly going to hand over to Andy, who can spend hopefully a couple of minutes just talking to the outcomes of all of this.
Yeah, thanks, Adrian. I hope everybody can hear me. As Adrian talked to, really, there's a lot of work that's gone into getting us to this point, to getting an understanding of the stabilization of graphene dispersions, and our approach, the end-to-end approach, talking right from the development of those dispersions right through to the application of those into existing industrial systems, has really given us a practical know-how of how to use these products to give real benefits in real existing industrial paints or composite systems. The examples here shown on screen, this is a library which is growing of our technical application notes, and they're all available on our website. As Adrian mentioned, it gives a real in-depth look at starting point formulations, test methods, and how to disperse, how to use the products, and really also gives a good understanding of the benefits and the results that can be generated through the addition of our graphene dispersions in a number of applications. It really is the kind of how-to guides of how to use the products. And then with that in mind, just give you some understanding of some of the success stories that we've had. As Adrian touched on, the graphene dispersions offer some very, very good, strong, outstanding performance in barrier systems, anti-corrosion systems. This example here is a company that we've been working with in the UK to solvent-based aerosol respray system for the automotive industry. A very basic primer in itself only withstood around about 300, 400 hours prohesion salt spray. And the graphene panel that you can see there is a 0.1% addition of graphene after 3,000 hours of prohesion salt spray. So around about a 4, 5, 6-fold increase in corrosion resistance. And as you can see from the photos, these are commercially available products that can be bought here in the UK. Another example on the next slide, Adrian, is a system that we're again working with a UK company. These are a corrugated steel roofing company. Again, a simple addition of our graphene paints at low loading levels, 0.05, 0.025% addition rates. Again, into existing systems, minimal reformulation work, just close cooperation with ourselves, with our technical team, to really understand how and when to add the graphene to maximize the performance benefits. And as you can see from the photo, they offer a 30-year guarantee on this product. That's an uplift from a 20-year guarantee on the graphene-free system. So it's a significant uplift in performance. The salt spray resistance is truly outstanding for this product. It's quite an exceptional product, right at the high-end performance levels of corrosion coatings. And then moving away from coatings, as Adrian touched on, into carbon fiber composite systems, we've got a couple of examples. This one is a simple carbon fiber pre-preg, where we are looking at increasing some of the mechanical properties, also offering light weighting. Still in moving into a commercial product at the moment, and offering some really interesting increases in fracture toughness, and also from a surface finish point of view, really giving a nice added bonus. And the final example I'll quickly touch on is a system that we're working with a company in the US. This is a cryogenic pressure vessel using the graphene dispersions in a couple of ways for a carbon fiber filament wound system. Again, showing some outstanding performance at some really quite extreme environmental temperatures and pressures. And it just demonstrates that if you work with the right dispersions, adding it at the right times, and really working closely with us to generate that know-how, you can get some quite outstanding uplifts in performance in a cross-section of applications.
Well, thank you, Adrian. Thank you, Andy. I appreciate that. You obviously have a wealth of knowledge and experience that you've accumulated, and so we definitely appreciate that. We do have a presentation now from Chromaflow Technologies, which have many, many years experience in working with nanomaterials and nanoadditives, and in particular have their expertise in dispersion technologies as well. So Paul, if you guys are ready to go ahead and share your screen.
So Chromaflow is a global manufacturer of colorant and specialty chemical additive packages and dispersions for the architectural, industrial coatings markets, as well as for the composites industry. We've been in business of making dispersions of carbonaceous materials on nanoscale for about 25 years. Some of our largest commercially sold products in the world are based on that type of technology. Give you an idea of our overview, we have multiple technical and manufacturing facilities spread throughout North America. Our headquarters and principal R&D center is in Asheville, Ohio, outside of Cleveland. We also have facilities in Sao Paulo, Brazil, and also in Uruguay. We have multiple technical and manufacturing facilities in Europe. Also, we are in South Africa. We have a significant facility in India, a brand new facility that we just built in Kuala Lumpur, Malaysia. We also have a facility in Shanghai, China, and also Dandenong, Australia. So we're literally prepared to cover and support our customers in pretty much every continent of the world. Some of the cases where we're involved with, we do work with architectural point of sales, architectural implant, coloring. We work with our industrial maintenance, concrete, automotive interiors, and refinish. We are both in the composites and the coating sides of the transportations and the constructions industry. You'll see here some pictures of some automobiles. You'll see some pictures of marine applications. We're involved in marine coatings, and we are also involved in composite materials, the construction industry, such as the composite ladders that you see in the upper right-hand corner. So in getting to graphene, there are two major approaches in industry to manufacturing graphene, and each of them has significant implications in terms of what you get when you get there, so to speak. The top to bottom approach involves starting with graphite and peeling down a number of layers until you get eventually to a graphene sheet. On the other hand, the other side of it, there are people that are taking, basically starting with carbon atoms, most typically and most commonly, but not necessarily by carbon vapor deposition, and then depositing the carbon into layers onto a substrate such as copper sheeting, and then removing the layers. And the latter, and which particular approach you get, each of them is divided into a significant number of sub-steps and sub-processes and variants and processes that are made, and a number of different types of materials that you can get from it can affect not only their cost, but also your purity and the properties of the graphene that you're going to get. So when we talk about graphene, it's not a homologous material. There's a lot of different materials that fall under the general category of graphene, and so we need to be aware of that when we begin to talk about how we make dispersions for it and talk about how we achieve the properties that we're trying to get. Several different types of categories of materials that can come out of graphene would include the graphene sheet itself, shown in this middle blue layer coming up and down. But another thing that can happen is you can also have the sheets roll into tubes that we would then call carbon nanotubes. And then also, finally, there's also the possibility for the carbon to come up into the balls and form carbon, what we call fullerene structures. This is all from the graphene hexagonal close pack structure that originally is coming from a planar two-dimensional object. Santosh, would you like to comment further?
Yeah, so I'm going to talk about how we're going to characterize this material, for the characterization, like the techniques, what kind of techniques we use to characterize this material. The first one I'm going to mention about the TEM, which is the high resolution TEM, which is a very good technique to get idea about the morphology of any nanoparticle. So if you look at this slide here, at the left side image shows the graphitic structure where you can see that we have like more than thousands layered, just like a stack on top of each other. However, when we look at the right side structure, right side image, you can see here we have just like a few layer graphene. So so the TEM provide you information regarding their morphology and particle size distribution, but that information is not enough to get idea about what kind of material you are dealing with. So you require some further characterization of the material. So the another techniques we use is called like XPS, and which is like also a good technique to characterize the surface chemistry. Like if you wanted to see that how what making change in that hexagonal the benzene ring, like if we are converting during our process, or like doing any chemical treatment, if we are introducing any functionality, or like anyhow we are changing that sp2 habitation to sp3 habitation. If you look at in this slide here, like the left bottom, we have it the table where we characterized two different material. One is a GNP, graphene nanoparticle, another one functionalized graphene nanoparticle. So we just put some functional group on that. You can see here how like the habitation like changing from sp2 to sp3, and their ratio is changing, and then concentration of oxygen containing moiety is also changing. So these techniques provide you information of the surface chemistry. And the next technique we talk about the Raman spectroscopy, which is very useful in the tool to evaluate the nanomaterial. So the Raman spectroscopy is kind of a vibrational technique that is very extremely sensitive to geometry structure and then bonding within the molecule. So if you are making any change in the geometry or in molecule, we can we can see that changes in spectra. So here we are showing in this slide we have the three different spectra from the same graphene product, but they are the different batch, different the lot. So you can see here like very we have the three different peaks there. First one around 1350, which is called the D peaks, and we call it disorder band, and that's the defect band. We also refer as a defect bands, and actually it represents the ring breathing mode from sp2 habitation carbon ring. So what is happening here, if we are creating some defects on the graphene, we can observe clearly here. We can see in the sample the green line, we can see the defects like getting higher. And also the same technique we can also use to characterize the graphene dispersion, and then the like the functionalization in order to see like if we are making any change on the surface chemistry, or like their structure, or like we are further exfoliating graphene. If like we started our starting material like a few layer graphene, if we do our process and we exfoliate somehow. So this is a really good tool to get an idea. And other peak is here, like the 2D peak. We call the 2D peak, which is like a 1700 the peak here, which provides like this peak have like a different kind of shape. By that shape, you can actually get we can evaluate like if we have a single layer graphene, or we are dealing like a multi-layer, or like the double layer. So that information provide, and that information is really helpful to determine either your like the graphene quality as well as your graphene dispersion. So now I'm going to talk about the challenges. What kind of challenges do you have to obtaining a stable, like a stable graphene dispersion? The first of all, I'm going to start with the quality of graphene. You wanted to make sure you have a very consistent the supply source for graphene, where you have like you without lot to lot variation, like, because we have seen experience like we have seen like a lot to lot variation in the graphene quality, and also like you wanted to make sure particle size distribution, and then control over particle size aspect ratio. And the second challenge, like we wanted to if you wanted to use the graphene for a particular application or particular resin system, so you wanted to compatibilize that resin, that graphene with the resin system. In order to do so, you might require some kind of functionalization, or some kind of additives, or any different any kinds of surface modification, or some special like the process or like some chemistry there. So the next one is the second one is the appropriate loading. We are talking about the appropriate loading. I'm going to talk about in the next slide, in a later slide, where appropriate loading is very important for the properties. So and then viscosity and the rheology also is important in that matter. And then process control. Process control is really important. It's very important how you are incorporating this graphene to your system. Like, are you like you're going to mix with using any kind of techniques, like either using sonication, that if you use very harsh technique or very rigorous the milling or any process method, that might create some defects and create some damage on the particle, which is further the line further like an end application that might translate in like not a better property. So that's very important there also. And the last one is proper characterization. How we're going to characterize if you have a really good quality, your dispersion is stable, and like you have you exfoliated your material, or you stabilize your material, or functionalize your material. So we already talked about the TEM and then STM and then Raman spectroanalysis. This is going to help to evaluate that one. And then next one, like a stability test, I'm going to discuss about that one. Like you can do some stability tests in your laboratory, or like to make sure you have a stable dispersion for a longer period of time. So, and then final one, property applications, like the property evaluation. So we can use like electrical conductivity or like other property evaluation to also verify, like if we have if you have a better dispersion, a good dispersion. If you're targeting for mechanical property, you will definitely see your end application. So Paul, do you want to add some comment here?
Yeah, I just want to emphasize that having a consistent supply and being able to verify the consistency of your supply of graphene is really kind of important. But when we talk about obtaining optimal properties in final application, a lot of that really depends upon process, and that means process from start to finish, right? I think one of the things Santosh will be mentioning later on is that's very possible to damage your graphene in your process, such as especially if you're doing by sonication or some type of technique that produces a whole lot of energy on individual particles. So viscosity control, impact on polymer chemistry, cure kinetics will all affect the processing of your material, because graphene itself is a chemical and it will interact with certain chemistries that are taking place in your system. Mechanical properties can come from better dispersion and high interfacial interaction. It's important to understand that what type of graphene dispersion you want to use, and what type of graphene and what type of loading you're going to use is going to vary according to the types of properties you're after. If you are looking for conductivity, electrical conductivity, what's very important is you have to have a very low percolation, right? But you have to have a good dispersion with a lots of point-to-point contact, because the electrons have to have a pathway in order to travel from one place to another. And if you disrupt that pathway, then your conductivity goes away. On the opposite hand, with mechanical properties, you don't necessarily, or thermal conductivity, you don't necessarily have to have point-to-point contact, but you do have to have a certain, what we might call heightened interfacial interaction. You need to have load transfer capability in between particles, so that the force and that the distribution of energy is maintained between the polymer matrix and also and the graphene particles that are dispersed within it. And I'm not going to have to take time right now to get into photon scattering, but the basic principle remains that you have to have an effective dispersion that's uniform and complete throughout your matrix if you want to achieve properties such as thermal conductivity. So back in 2013, Professor Yadav and others at the University of Konkuk in Seoul, South Korea, did a study on comparing graphene that had been chemically functionalized to be compatible with a urethane matrix, and compared it to what happens when you add pristine graphene in its place, and you put that into the same urethane composite matrix. They discovered that if you have a good interface between a polymer, then you can see it under SEM, and you can see that the sheets of individual graphene have a high level of bonding with a strong interface between the urethane polymer and the graphene itself. If you have a weak interface, then it's very possible, as we see in the right-hand image, for the different particles to get broken apart and be separated, and then you don't have basically, you're losing what we would call load transfer. A more graphic demonstration of this is the following image here on the left-hand side. The functionalized, optimized graphene dispersion in the matrix remains embedded upon breakage into the polymer matrix, whereas in the material that has not been optimized, where the graphene is not properly incorporated or functionalized for the matrix, the polymer simply breaks away from the graphene platelets, and you don't necessarily get the benefit of the platelets in terms of making a meaningful contribution to your strength. So on that note, one of the ways we can determine or verify the properties of our dispersion is through simple application testing, right? And one of the things we would do is especially for electrical applications, we have three major methods of measuring electrical resistivity methods. One is a one-dimensional point-to-point in linear ohms per centimeter. Then we have a two-dimensional, which is ohms per square. And then we have a three-dimensional method that's in ohms per cubic centimeter. And it's important to understand that as we increase the surface area of contact and number of dimensions in our measurements, we increase the sensitivity and reproducibility of our tests, as well as the number of pathways available for free electrons. So when we do this type of analysis, one of the issues you're going to run into with a non-stabilized graphene dispersion, you can load it up and increase the loading, and you're not going to get to a point where you have high enough loadings of percolations of point-to-point contacts between graphene to achieve a static dissipative conductivity. And we see this in the left-hand chart, where we're increasing the graphene loading to almost 3%, and it's not making a significant change to the resistivity in three-dimensional or one-dimensional resistivity. By contrast, if we have a stabilized graphene dispersion that's compatibilized with a polyester graphene matrix here, then what will happen is you point somewhere between 1 and 1.5%, where the graphene will begin to percolate, and you'll begin to achieve point-to-point contact, and thereby you will begin to achieve the electrical conductivity that you're trying to achieve. Especially in this particular case, you're going to get to a static dissipative level of conductivity very quickly in the 1.5 to 2% loading range. Santosh, do you want to comment on the stability testing?
So yeah, this is the simple stability test. Like when you can see the difference between we have the two vial here at the right side. you can see that if you stabilize your graphene or like you disperse them well, they're going to stay for a longer time in any like a solvent or like any monomer or polymer. They're going to stay for a longer time. So they allow you to have like you can process like if your process involved for a longer time, or you can store these samples for a longer time also, and use them for your application. So next, I'm going to talk about the mechanical property. Like the Paul already mentioned about that how like the interfacial interaction between graphene and polymer matrix play a role to translate to load transfer the mechanical property to in the polymer system. So here you can see we have example like where we take a functionalized graphene and just like the raw graphene and just added in the like a polyurethane elastomer, and we observe like a very high modulus enhancement that was several fold enhancement in modulus and other property also. So that's like a loading was like up to 3%. We could achieve like the modulus to 113 megapascal. So it was kind of when you have like a better dispersion as well as a good interfacial interaction between graphene and your host matrix, then it will have like a better load transfer. And next slide, I'm talking about like here giving an example of this like a stabilized dispersion in a pultrusion system, where a polyester, we took a polyester and then added the graphene like at the different loading. Earlier I was talking about like how important it is to determine like optimize your loading. So you can see this the left side image that is the storage modulus, room temperature storage modulus value of polymer composite. And what we observe here when we incorporated the graphene, like, starting from 0.01% to all the way 3%, and we observe that we could achieve like a 30% enhancement in storage modulus value by adding 0.5% graphene dispersion. However, beyond that, like when we add 1% or 3% graphene, we saw like detrimental impact on the storage modulus value. So we know we need to find this, and that's kind of sweet spot where you can get the maximum, the load transfer, and kind of you have the balance between filler and polymer matrix. And here, like the right side of image here, we are showing very interestingly when we added even to 1% is not impacting the cross-link density of the polymer composite. So we don't see any change in TG. There was like a few degree up and down, but here we see when we add like 1% graphene, we even see further boost in the TG. However, in epoxy system, when we added the graphene dispersion in epoxy system, we see here we could achieve like 28% enhancement in storage modulus value just by adding 0.1% graphene. And however, beyond that one, we see like again decrease in the storage modulus value. So it's all depend on like what kind of stabilization you are using and how you are processing the graphene, and what kind of polymer matrix you are using. And here also we observe there was few degree like a change in viscosity, with saying that with suggesting that there was some change in cross-linking density in composite after adding like a few percent of graphene. So here, this is just like we are giving quick the view here. We have several graphene dispersion where like we have developed several graphene dispersion, like they are very highly loaded, like we have like 28% to 36% graphene loading in the different the carrier, like polyol, DOPT, and some the polyester resin system. So and you can see here we have like the wide range variety of viscosity and Thix index. This is just an example, and we do also some like customize customize the product where we take the customer resin and then disperse the load the graphene, make the master batch and provide them for their the end application. So at the Chromaflow we have like like graphene dispersion, like high loading graphene dispersion in monomer, plasticizer, water, the solvent base is styrene, and polystyrene, epoxy, polyol. So what basically we are providing here, like providing the dust free dispersion to customer. Like there are many in industry, many people, they're not capable of dealing to handle this nanoparticle because you have a lot of EHS concern involved there. So, and then also it's well dispersed and stabilized dispersion, which promote homogeneity in final application. And then quality control, we make sure that you get the consistent, there's no lot-to-lot variation in performance. And also our dispersion is compatible with other different kind of resin system, different kind of the host material. So, and we also support to customer to provide the methodology to incorporate these graphene dispersion into their system. So Paul, you wanted to add some?
Yeah, I think you've actually covered it very nicely, Santosh. The thing I want to emphasize is that the process from start, from your manufacturer's process, your supplier's process, to your internal mixing or incorporation or dispersing process, through the final application of molding and or coating or application process, every step of the process makes a difference, and every step of it is going to be very important to achieving your final properties. If you need to reach us, we are located in our Chromaflow Technologies in our Ashtabula, Ohio facility. My phone number and Santosh's is listed here, and as well as our email address if you'd like to reach out to us with any questions. And we'd like to thank you also for your patience and your participation. Thank you.
Gentlemen, thank you both for that. We're going to go to Q&A right now. And so we've got quite a few questions. I think one of the things that always strikes me when we look at graphene dispersions is both of you have, both companies have presented on the extremely small or low load factor, so tenths of a percent by weight, and yet getting these 20, 30, 40% improvements in performance, whether it's in strength or barrier properties and such as that. So one of the questions that always comes up is, what is the impact on cost, right? So if you're looking at these extremely small load factors into the end products, and I don't know, Adrian, maybe you can touch on that first, but I'm sure that many customers, when they hear about the nominal price of graphene is not inexpensive, but when you look at the percentages in the end application, it's quite a small amount, and you're using standard processing approaches. What is the impact on price? I mean, how should customers look at whether they add graphene from an economics perspective?
Yeah, sure. So, I mean, just to talk to that, I mean, clearly there's the end-to-end discussion to have. You're looking at materials performance enhancement with a remarkable material that can be transformational. And yeah, there's a cost associated with that. We've done a huge amount of work looking at various stages of that, Terence. So, there's a cost to a dispersion, and where somebody wants a quote, I have to give you a quote for prices for dispersion. That's fine. Clearly, if we're looking at say a 10 or a 20% dispersion of a graphene into solvents or waters or a resin, then there's a dilution aspect to that. And, clearly you've got to understand that say you're adding that into a matrix resin that's part of a component of a composite material, for example, which we do often as a customized dispersion, then you're looking at the cost of that whole dispersion, but you're actually substituting the resin that you get in the dispersion with the resin that you would be putting in the composite anyway. And to really get to the nub of the question, is this stuff affordable for the technology gain that you make? I think there's a judgment call on that with regard to what you're trying to put it into. So in the coatings arena, for example, where graphene, you could say there are areas of the coatings community that graphene has no real technical advantage to an addition, and it's a hugely competitive market. Why would you even think about doing that? At the other end of the spectrum, where there's an added value opportunity for the technology gains that you'll make in the coating, say for an ultra harsh environment coating, where there's performance gains to be made and there's the cost of the graphene that you're adding to that scenario, we believe it's an affordable proposition. But you also, I think, not to forget in all of this, the knock-on effect of the end user, so our customer's customer. Right. So if you look at, for example, an infrastructure project and a coating on a bridge, is that bridge going to, or the coating on that bridge, going to last longer to reduce the maintenance cycle that the asset owner has to undergo? There's joined up thinking. So yes, there's a price point to anybody's graphene in this community. We believe that we can make an affordable value proposition for that, and in terms of added cost, if you're looking at something that's sort of $60-70 a kilo material cost for a coating system, you're looking at a few percentage points of addition, and right. you've got to the graphene actually through the dispersion and into the coating system. And that's similarly true for a composite or anything else you want to look at. In thermal adhesives, it's somewhat of a different proposition, I would say, in that you're looking at extremely high loading levels. So
well, Adrian, the examples that you gave in your presentation, if you look at the salt test on the paint coating plus the roofing product, right? The roofing product had a 20-year lifetime guarantee from that supplier until they used your material. Now they've increased that to 30 years. So that really gives them a competitive advantage in the market. And if we look at some of the marine coatings, so there's companies like yours and others that are using graphene for marine coatings. It's not just that, the added corrosion protection gets translated into a ship going into dry dock less frequently, which has a huge economic impact. So I think if you look at the total cost of ownership, or if we look now in composites, life cycle, the complete life cycle of the materials, how long do they last, their utility, when do they become redundant, when does it get, when does it need to be replaced? If you can extend the life cycles, there's some, ecological improvements to be made there. So, yeah. Paul, let me ask you, a similar question. I don't know from the economics, because you're dealing with end customers all the time, doing their custom formulation. So obviously, it's always a question of price versus utility. What's been your experience in looking at materials like graphene and added from an economics point of view?
Well, first of all, graphene is not a homologous material. There's a wide ranges of quality and cost structures out there in the market. Sometimes it makes sense to go ahead. For example, if you're going to improve your properties by 30% and reduce the weight of your part by potentially 30%, and the thickness of your part to achieve similar or better mechanical properties, sometimes it makes sense to use it's more cost effective to use the more expensive graphene than to use a more cost effective graphene. So it really depends upon your application. Similarly, in a coatings application, you really want to have a very fine layer of graphene across the surface of your coating, and you want it to be located at the surface where you're going to get the benefits, right? So you don't necessarily want a real high loading, So again, going with quality and cost, I think you're going to get a better bang for the buck. And then again, you also have to consider in, as has already been mentioned, the impact upon shelf life and usage life of the material. If you're extending the usage life of the material by an extended period of time, reducing the amount of money someone's going to spend on recoating and repainting a part in the field, that is huge.
Right. Absolutely.
And so I think you really have to assess the whole cost of the whole process and the whole product when you're trying to say, oh, is it going to work for us to use graphene? Maybe I should just use something cheaper. Well, maybe something cheaper isn't going to do the same job.
Right.
Or it's cost effective.
Another question, we are looking at commercial application and commercial scale of these products. So one of the questions is, how sensitive is this process to do the dispersions? Does it need to be done under ideal lab conditions, or obviously in production processes, they're not always, let's say, ideal conditions? So how sensitive is this dispersion process, and how do you address some of those variabilities that you get in the real world where, the product might sit in a warehouse, you've got temperature variations, you might not have the best environment in which to do the dispersion? Can you speak to that? Maybe Paul, do you want to start with that one, or Santosh?
Yeah, I'll go ahead and get started on it. First of all, when you're talking about manufacturing in a real world environment, graphene is not your normal dry powder that you just toss into something, right? There's EHS considerations, there's worker safety considerations, there's a lot that has to go into controlling your environment and your process for making it. And secondly, you also have to, without getting into the EHS side of it, you also have to be concerned about the technical quality side of what is the impact of your process to the particle. And we spent some time showing some examples where you have improperly dispersed graphene and you don't achieve the end properties you're after, then you spend a lot of money on a fairly high cost product and to come up empty. So you don't really want to get into that scenario. It's much better to have a well-designed process that gives you a robust, that's inherently robust and gives you a robust product that will stand up to a wide variety of conditions. Now, in terms of like putting in a warehouse and storing it, if you achieve a good stable dispersion, hopefully you do the stability testing, at 40 and 60 Celsius or some such to verify that you achieve, that your material is going to be stable for an extended period of time under a variety of conditions.
Excellent.
So that's kind of the answer I have to that one.
And
Adrian, do you want to add to that?
Yeah, clearly keep coming back. It's all about end-to-end thinking, and being aware. We put a huge amount of effort in engaging with the end customer. Not just about what we do in the lab, but how they are going to use this material. So, whether it's going into a coating, a composite, whatever it is. And we've got a range of customers, where their process conditions on their actual shop dictate that they have to add this dispersion at a certain point. And so, the part of the process is helping the customer to understand and to further customize our product in some cases, to actually enable them to integrate this material in what they commonly do. If you've got to introduce a lot of change to introduce a new material, you've got a question, are you actually going to do that? So, we in terms of our approach, we want to be as aligned as we can be with our customer in terms of how they're going to utilize this product. And to your other side of their question about what we do. So, we do a huge amount of work in terms of all of the, as we were talking about before, the salt spray testing, the this and that and the other, 6 months, 9 months, a year's worth of work of proving that graphene works in a range of applications. And we do that in our R&D labs. Clearly, there's a scaling aspect to that, and we equally put in the effort to make sure that what we have scaled in terms of getting to high volume scaled manufacturing is representative of all the lab work that we did in the first place. Otherwise,
Right.
if you process it the age-old adage, I suppose: make a change, expect a change. And
Yeah.
you know, if you change your process, are you going to still end up with those same aspects of materials, such as particle size and you know, viscosity profile, and so on
Yeah.
and so on
Yeah.
and so on.
There's one last question I'd like to take before we kind of close off here today. And there are a ton of questions we're just not going to get to, but one is about, you know, is there some kind of like guide or rule of thumb about, you know, which graphene is best for which type of application for which type of attribute that we want? And I think I know the answer to this. And of course, you guys do know the answer to this, is that there's so many different types of graphene. The detailed morphology is so different that I don't think we're yet at the stage where there's a common body of knowledge that's kind of like a dictionary or a directory of, okay, if you want to get this outcome, then this is the type of material you use. But by the same token, we don't want to give the impression to everybody that this is some black art and that only a few people know the secrets to the kingdom. There's some pretty straightforward approaches to this. But the fact that at this particular stage, there are many different types of graphene that are manufactured. I think the important point I'd want to try to convey, and like to have you kind of comment on this, is that we've moved beyond the stage of, you know, this is purely experimental, and that there are some proven results that we know graphene can truly enhance in a commercial setting these attributes. It's real world. We've moved beyond that kind of pure R&D stage. We're into the commercialization. And the project, again, that we're doing with Chromaflow's help on testing actual pieces of composite materials to demonstrate, you know, some of the physical attributes, is going to go a long way to provide some more public data on those. But you've obviously, these two companies, and the reason why we've chosen these companies to help do this presentation today, these companies have obviously accumulated a huge body of experience and knowledge in how to do these dispersions. I'm not sure really where the question lies at this point, but would you like to make just a couple of maybe closing remarks on this particular topic about dispersion, why it's so important? And my last comment on this would be, you know, I would encourage customers that want to use this material to engage closely with companies like Applied Graphene Materials and like Chromaflow, who have the experience and can assist you in avoiding a long and tortuous and expensive self-discovery period to get through this. This is, they've gone through working with, you know, hundreds of iterations of these materials and all different host materials to figure out what actually works. And that is their, you know, their expertise and their IP. So Adrian and Andy, you guys want to make some closing comments on what we've discussed today?
I'll let Andy comment on it a bit further, perhaps, but all I'll say is, yeah, 10 years in the making, as I touched on at the start of our presentation. You know, we've been doing this for a good while, just in terms of looking at initially the sort of twinkle in our founding professor's eye about an alternate way of making graphene, through to process scale up for that material. But the last few years have been completely focused on dispersion technology and the how-to, and how to actually join the dots, in simple terms, about taking this remarkable material, whether it's our material or whether it's anybody else's material. I fundamentally believe that the keys to that are in being able to put it into the right stuff for it to end up in the customer's formulation, whatever that might be. Andy, you want to talk any?
Yeah, no, I mean, for me, you touched the right point. I mean, graphene as a product is a fantastic product, but as soon as you put it into something, a lot of those properties are lost in a lot of cases, and certainly diminished. If you get your dispersion right, you get your application method right, then you can benefit from a lot of those properties. And, you know, like I say, we've done a lot of work on this. The guys at Chromaflow have done a lot of work on it. So it's almost, why reinvent the wheel? You know, come and talk to us. You know, we're very open in terms of those communications and those conversations. We can have that and optimize your system so that you can get graphene into it, the right graphene at the right loading levels, at the right costs, to make sure that you get a benefit.
Yeah, I would like to just add there, like, you know, it's just not the the graphene quality matters. It's a matter how you incorporate, how you process, and what is the loading. So all like hold the process there. It's just not the magic material. You take it and put it anywhere, and you're going to get your the final property. So everything matters. Yeah.
There's one more point I want to add to this. There's a slide that Santosh showed everybody that I think really hits the nail right on the head. If you get the graphene dispersed and you put it into a matrix, you can sometimes see a night and day difference when it's properly dispersed, when it's not, simply on how it behaves within the matrix. If it doesn't behave within the matrix properly, you're going to see like a thin cloud of flocculation. We get down to the particle size that we're talking about here. Say we spend a lot of time talking about particles that are in a neighborhood of 5 to 10 carbon atom layers in the surface, width, breadth, and so we're talking about something that we're almost leaving classical physics, moving into quantum mechanics, and forces like van der Waal that are normally not all that strong a force start to become really predominant. So recognizing that and not treating a graphene particle or graphene product like a standard, say, carbon black is really kind of fundamental and very important. So I'm just going to leave it on that particular slide.
From the Graphene Council perspective, I really appreciate everybody sharing. I want to just leave everyone with this slide. If you look at this, this is one of the reasons why graphene is so exciting, is it can be used in all these different application areas for many different outcomes, whether it's electrical conductivity, thermal conductivity, increasing strength, etc. And both organizations, both Applied Graphene Materials and Chromaflow, touched on that as well in their presentation. So I just want to bear in mind, because we have people from all over the world, all different industries listening in today. For the Graphene Council, those of you who are not a member of the Graphene Council, things like this webinar, but in particular our graphene report, and more importantly, our ability to help you connect with the supply chain will help you reduce your R&D costs and get to an end application sooner rather than later and at less cost. So I'd encourage you to think about becoming part of this environment. We connect more than 27,000 material scientists worldwide. We have special benefits for organizational members, which include universities as well as companies. So for myself at the Graphene Council, I want to thank Adrian, Andy, Paul, and Santosh for taking the time to prepare this information. I hope it's impressed upon people who are watching today. The type of information you receive from these two companies really is valuable. It is critical to successful applications, and I appreciate them sharing their insights, which literally have taken years and years to accumulate that knowledge. So thank you for that, and thank you for everyone for paying attention, and wish you a good rest of your week. Thank you.